So often in science we'll take a bunch of measurements and then we'll do some math on them. And we want to make sure that we're doing our math in a way that doesn't sort of result in us generating numbers that overestimate or underestimate the quality of our measurement. So in our very first experiment in Chemistry 161, we're going to be determining the density of an egg. And to do this, we'll take the mass of a substance and we will divide it by the volume of that substance and we'll calculate the density. So the question is how do we make certain that our density ends up with the correct number of digits, that it doesn't overestimate or underestimate the quality of our measurement? So to do this correctly, we need to apply what are known as operational rules to determine how many significant figures our answer should have. And there are two of these rules. The first one applies to division and multiplication, and it says that our answer from either division or multiplication should contain the same number of significant figures as the measurement with the least number of significant figures. So when we're multiplying or dividing, it's all about the figs, all about the significant figures. So let's have a look at a little example here. I've got 26.003, that's a mass measurement measured out to 3 decimal places, just like our balance in the lab. And then here I've got a volume measurement measured to 1 decimal place, just like our graduated cylinders in the lab. So this guy here has got 1, 2, 3, 4, 5 significant figures, and this number here has 3 significant figures. So my answer has to have, because I'm dividing 3 significant figures, so you can see here I've given my final answer to 3 significant figures. Now, I have a second rule that applies for when I'm adding or subtracting. And when I'm adding or subtracting, it's not about the significant figures, it's all about the uncertainty, the plus or minus of my measurement. And my rule is this: for adding and subtracting, the answer has to have the same uncertainty, the same plus or minus, as the measurement with the greatest uncertainty. So here I'm adding two masses together. This is a really common thing to do, to take a container and then to put some stuff into it. So what we've got is our total mass here is the mass of this ship, which was measured to be 207.1 tons. So that tells me that my uncertainty is plus or minus 0.1. It's plus or minus 1 in the last digit there. And then the mass of my cargo is 26.003 tons. So my last significant figure is the 3 there. So that uncertainty is plus or minus 0.001. So this guy is the biggest of those two numbers. So when it comes time to write my answer, I'm going to give my answer to the 0.1 position. So my answer has the same uncertainty as the measurement with the greatest uncertainty. So that's really it. You can sort of apply these two rules. So let's have a look at this question here. It's asking us, without performing the calculation, which is kind of sometimes common, predict the number of significant figures that should be present in the answer. So we've got to decide, are we multiplying and dividing, or are we subtracting and adding? So in the first problem here, we're only multiplying, so it's all going to be about sig figs, right? It's all about the sig figs. So this guy's got 3 sig figs, this one's got 3 sig figs, this one's got 3 sig figs, so they're all equal, so my answer is going to have 3 significant figures. Okay, so that's really it. Again here, I'm multiplying. Every operation I'm doing here is multiplying. This number here, 3 sig figs. This guy here, 2 sig figs. This one here, it's got a decimal point there, so my trailing zeros do count. So I've got 1, 2, 3, 4, 5 sig figs. As I'm multiplying and only multiplying, my answer's got to have 2 sig figs. Okay, so again here, we're multiplying. These leading zeros don't count, but this trailing zero does because my number has a decimal point. So I've got one non-zero number and a trailing zero, so that guy's got 2 sig figs. My operation is multiplication, in both cases. Again, these leading zeros don't count. I do have a decimal point, so this whole number, or this number that is greater than 0 and this trailing 0 counts. So again, I've got 2 sig figs. And here, we've got these leading zeros, they don't count. And then I've got these two non-zero numbers, they do count. So I've got 2 sig figs, so my answer is going to be 2 sig figs. Okay, so in the final one, again, I'm only doing multiplication. This number here, my buried 0 counts, but my trailing 0 doesn't because there's no overbar and there's no decimal point. So this number has 3 significant figures. This number only contains non-zero numbers, so there are 4 significant figures. And this guy contains 2 non-zero numbers and a buried 0, so this number here is 3 significant figures. So that means that my answer is going to have 3 significant figures for 3, 4, and 4. Okay. So again, now we're doing the same thing without performing the calculation. Give the uncertainty of the answers to each of the following. And assume all numbers are measured quantities. That means that they're not exact numbers. And so what we're working on here is we're working with adding and subtracting. So this one kind of looks like there's a little bit of an issue there that it doesn't have an addition sign in there. So I'm just going to draw it in for you. And so here we go. We've got 13.1, 13.001, 13.010, and we're looking for, it's all about the uncertainty in this case because we're looking for what one has the biggest plus or minus. This one is plus or minus 0.1, and then these last two are plus or minus 0.001. So this is the guy that has the biggest uncertainty, so that's going to be plus or minus 0.1. Okay, when I head down in here, I see that this number, again, I'm adding and subtracting, so it's all about uncertainty. And what I see here is this guy is plus or minus 0.1. This one is plus or minus 0.01. But this number on the end here is plus or minus 1. So the uncertainty in the answer to this should be plus or minus 1. Okay, here we've got some numbers that are smaller than 1. And this guy has uncertainty in the last digit here. In this case, the trailing zeros are significant because my number has a decimal point. So my uncertainty here will be plus or minus 0.0001. And then it's the same uncertainty over here, plus or minus 0.0001. So I need a decimal point, 3 zeros, and a 1. Alright. So in D here, it's a little bit different because we have a trailing 0 that isn't counted in this first number here. So this first number here, where we're in this addition, our uncertainty is going to be in the tens position. So that's going to be plus or minus 10 will be our uncertainty. In our next two numbers, the uncertainties are much smaller than plus or minus 10. In this case, it's going to be plus or minus 0.001. And in this case, it's going to be plus or minus 0.1. So our uncertainty for our final number there is going, for our final addition there, will be plus or minus 10. So there becomes a little bit of a difficulty when we're doing these calculations because when I put my measurements into my calculator, it's not going to return it with the correct number of significant figures. So going back to that density calculation before, here's my mass measured out to 3 decimal places, and this is my volume measured out to 1 decimal place. The calculator answer that I get has many more than 3 significant figures. So I know that my answer should be truncated at the 3rd significant figure. That is that I should have my answer should be cut off after the 4. And the question is, well, what do I do with these numbers? Do I just kind of get rid of them, or how do I take them into account? How are they important or not? And so what do I do with those numbers? So we have to use rounding rules in order to help us deal with these numbers that we are truncating or cutting off. And we have two simple rounding rules and then a third one that's a little bit more difficult. So if the first number is being dropped is less than 5, and then we just drop all of those numbers. So here I have 6.234. I want to round that off. I want to cut it off after the 3 there. So as 4 is less than 5, it just becomes 6.23. My second rule is that if the first number being dropped is greater than 5 or is equal to 5 followed by digits other than non-zero, so basically like 5 and a bit, then I'm going to increase my last value by 1. So here I go, I want to cut this guy off at 3 significant figures. 7 is bigger than 5, so I'm going to take this up to 62.4. Here's another example here. I want to cut this off to 3 significant figures. So I've got a little bit more than 5 following the 3, so the 3 gets bumped up to a 4 again. So the important thing to keep in mind is we either leave the last digit alone or we increase it by 1, but we never actually ever decrease our last digit by 1 or any other number. Now this is where our third rule gets a little bit complicated. If the first number being dropped is exactly 5, or alternatively it is 5 followed by just a bunch of zeros, then we use our odd and even rule, and that is we're going to increase the last digit that we're keeping by 1 if it is odd, and if the last digit that we're keeping is even, we're going to keep it the same. And something to keep in mind is that a 0 is considered as an even number. So here we go, we're going to round this guy off at the 5 here, and it's being followed up by exactly 5. So 5 with a bunch of zeros, and so we're going to increase this guy by 1 because the digit that we're keeping here is the 5, the last one, so that's going to become 46. In this case here, again, we've got the numbers that we're getting rid of is a 5 followed by a bunch of zeros, but the last digit that we're keeping is an even, so because 4 is an even. So for even, we keep it equal, so that's how I remember that, even equals equal, and so we're going to leave that guy at 44. Here's another example. We're going to cut this off at 3 significant figures. It's exactly 5 that's following our last significant figure, and our last significant figure is an odd, it's 7, so odd goes up by 1, and then that becomes 368. Okay, there's another 2 examples here. In this case, we're cutting it off at 4 significant figures. The last digit that we're keeping is a 2. It's followed by exactly 5. 2 is even. Even is equal. We're going to leave it alone. Alright, this one's a tricky example. The digit that we're going to cut this off at 3 significant figures. It's followed by exactly 5, and it ends in a 0. There's a couple of things going on here. 0 is considered even. So, for evens, we keep it equal, but if we wrote just plain old 350, that would actually be 2 significant figures. So what's important is we make sure that we either put a decimal point at the end of our number, or that we put an overbar over our 0 in order to get our 3 significant figures. Okay, so that's our rounding rules and how we kind of deal with significant figures within calculation.